Welcome, everyone, and thank you for joining today's webinar, Integrating InSAR into Engineering Geological Practice, Urban Excavation and Slope Failure, Case Studies from Italy. We're glad to have you with us today. My name is Christina Goring, and I'm the Manager of Customer Success here at PCI Geomatics. I'll be your host for today's session. I'm joined today by Dr. Ben Conway-Jones, an InSAR scientist at PCI Geomatics, who works closely with clients throughout the full project lifecycle, from initial project scoping and data processing through to analysis and final delivery. Before we begin, just a few quick housekeeping notes. All participants are currently in listen-only mode. We would appreciate it if you could take a moment to complete our short poll. Your feedback helps us better understand customer needs and guides future improvements. If you have any questions during the session, please submit them through the Q&A panel. We'll answer as many as possible at the end of the presentation. Today's session is also being recorded, and we'll share the recording afterwards, along with responses to any unanswered questions. Today's webinar will focus on the application of InSAR in urban excavation and slope failure monitoring. I'll begin with a brief introduction to Catalyst before handing things over to Ben, who will walk us through the Milan Metro Line 4 expansion and the Niscemi landslide case studies. These examples demonstrate how satellite-based deformation monitoring can support construction oversight, risk assessment, and geological interpretation. Following the presentation, we'll open the floor for questions, and the total session time should be approximately 45 minutes. Catalyst is a geospatial software platform specializing in remote sensing, photogrammetry, and Earth observation across both optical and SAR imagery. For more than 40 years, we've helped organizations transform complex geospatial data into operational information through advanced image analysis, orthomosaicing, and scalable processing workflows that integrate into existing systems. Our mission is simple: to turn geospatial data into practical intelligence that supports better decision-making for a thriving planet. Catalyst develops Earth observation software in collaboration with satellite providers, governments, space agencies, and academia to support EO applications worldwide. Our portfolio focuses on two core areas: image processing and risk monitoring. Image processing is at the core of what we do. Our tools, Catalyst Professional, Enterprise, and Onboard, help organizations turn raw imagery into usable data, whether they're operating on desktop systems, enterprise environments, or in the cloud. We make it easy to process large volumes of multi-sensor imagery while keeping workflows efficient, consistent, and cost-effective through connected systems and automated pipelines. Building on that foundation, Insights combines various data sources through AI-powered analytics to help organizations monitor and respond to risk. The platform supports applications across infrastructure, insurance, agriculture, mining, transportation, disaster response, and forestry, allowing visibility into environmental and geospatial activities. At the core of our software is a strong scientific foundation built on proven algorithms used across a wide range of industries and applications. One of the key advantages of the platform is that it is completely sensor agnostic, allowing organizations to choose the best data source for each use case or to combine multiple sources for a deeper analysis. The platform supports more than 100 sensors and over 750 algorithms, giving organizations the flexibility to work across both cloud and desktop environments, while integrating with providers such as AWS and Microsoft. We've had the opportunity to support teams across a range of industries. These are some of the organizations we've partnered with across government, defense, and commercial sectors. They represent a wide variety of use cases, but more importantly, the level of trust that our platform has earned. Across these teams, our software is used in real-world operational environments, supporting everything from API-driven applications to automated workflows and OEM integrations. The workflows supported within Catalyst extend far beyond InSAR and the examples that we're going to show in today's webinar. They include orthorectification, object-based analysis, mosaicing, DEM generation, change detection, and many others. If you have an upcoming project or are evaluating new datasets, we'd welcome the opportunity to work with you to explore workflows and demonstrate capabilities tailored to your specific objectives and requirements. And with that, I'm pleased to introduce today's speaker, Dr. Ben Conway-Jones, who will present the 2 case studies.
Fantastic. Thank you, Christina. So as mentioned, I'm going to go through a couple of case studies based in Italy, the first of which is the Milan tunneling study. For those of you that perhaps haven't worked with InSAR data before, what we're doing is using satellite data to measure deformation at the surface. So there's a GIF in the right-hand side here that shows satellites orbiting around the Earth acquiring radar data. Radar satellites work by emitting a radar signal. That signal reflects off the surface. And then the satellite measures the signal that returns back to the satellite. One of the things we can measure is amplitude, or the strength of the response, and that's what's shown in these black-white image here, and that tells us a lot about the surface properties. But what we're interested in for InSAR is the phase, and that's shown in the bottom left-hand corner here. So when satellites fly over an area of interest, they emit the radar wave, that wave bounces off the surface, and when it returns back to the satellite, that signal will finish at a certain point on the waveform. That in itself isn't terribly useful, but what is really valuable is that when that satellite disappears and comes back again, say 6 days later, flying over the same area of interest, when it emits its radar signal, we can then look at how that phase changes. So in our example here, between the 2 images being acquired, we see an episode of subsidence. And so when it emits that signal the second time around, that wave has slightly further to travel, which means that when it returns back to the satellite, we have a slight shift in the phase. As we call that the phase shift. And so we can then use our knowledge of the wavelength, the signal we sent down, to determine what the displacement is at the surface with millimetric accuracy. We're using these radar satellites that orbit hundreds of kilometers above the surface of the Earth to measure millimetric displacement at the surface. This is done using a combination of both Catalyst professional software, but also our in-house proprietary InSAR algorithms. So, as I mentioned, the first case study I want to look at is the M4 subway tunnel in Milan. This was a really complex urban project with over 15 kilometers of tunneling beneath Milan's historic centre. And the tunnel boring machine passed within meters of national landmarks. On the right-hand side here, you can see the path that the tunnel boring machine took. And this was a really challenging construction. Liquid nitrogen was used to freeze and stabilize the soil as the tunnel boring machine went through, and over 600 buildings were monitored on the surface. Because this was such a challenging construction, it was a long-term project. It began in the early 2010s, and it wasn't fully open until October 24. And in a project like this, InSAR provides continuous, remote, wide area monitoring with millimetric accuracy, flexible reporting for long and complex projects. So finally, to look at some InSAR data. On the left-hand side, we have our InSAR result. So this measures cumulative displacement from 2019 through to 2021. Each colored pixel is where we have a measurement. Green is showing us that we have near on 0 cumulative displacement. Red is movement away from the satellite. So this is a 1D result. Because data or satellite data is acquired at an angle as opposed to directly overhead, when we just look with a single line of sight, we obtain a 1D measurement, which is movement towards or away from the satellite. If this was purely vertical movement, then red would be equivalent to subsidence. We are able to determine pure vertical movement, and I'll show you that in the next case study. The red is moving away from satellites, blue is moving towards, and it's scaled to plus minus 15 millimeters. So where we're seeing these darkest red points, where we see these darkest red points, we have 15 millimeters of displacement between 2019 and 2021. And what's amazing is that we see this really strong correlation between a pattern of displacement and the tunnel that was bored. And this is because we are essentially tracking the displacement at the surface caused by the tunnel boring activities within central Milan. But we can do plenty of other things with InSAR data other than just look at cumulative displacements. And to do that, we're going to go into our Insights platform. So this is the platform that we deliver all of our InSAR data to our clients. It has all the usual GIS bells and whistles, turning layers on and off, changing color scales, opacities, that sort of thing. We have a number of tools specifically designed for interrogating InSAR data. One of them is time series. So what we're seeing here is displacement as a function of time. Because we acquire these radar images every 6 days or so, that's when we could add a new point onto our time series every 6 days. On the x-axis of each of these, we have time. So we go from January of 2019 through to the end of 2020. And on the y-axis, we have cumulative displacement from 0 to minus 20 millimeters. If we take a point on the eastern side of this line, we can see that actually, while we do have 15 millimeters of cumulative displacement, that's not a linear or a consistent trend. Most of that actually occurs in just a couple of steps that last days to weeks. And so these are a pretty dramatic displacement trend over really short periods. And if you look at other areas of the line, so for example, on this red line here, and we've got another blue one over here, we can see the same trend, that more of the displacement happens over a very short time period. What's also really interesting is that the signals here are staggered. So on the eastern side, it happens in July of 2019. Then in the south, it's in January of 2020. And then finally, July of 2020 at the westernmost point. And this is because we're tracking the tunnel boring machine. This displacement at the surface is associated with the tunnel boring machine passing beneath. And as that tunnel boring machine moves, we get this displacement signal at the surface. And we could track it in this GIF. So on the x-axis at the bottom here, each blue dot is a radar image. And we have a moving 6-month window in which we're looking at that displacement. So the start of 2019, we can see displacement towards the east. And then we can follow this displacement signal all the way south and then to the west during the tunneling activities, tracking the tunnel boring machine. I think this is a really powerful example of how InSAR is capable of detecting millimetric displacement at the surface for really complex urban projects. I think this also shows another aspect of InSAR that's really powerful, is that we're looking at the whole area the whole time. So even when the tunneling is occurring on the western side, which is presumably where a lot of the ground-based instrumentation and certainly a lot of the attention will be focused, we're still monitoring the east, where the tunnel boring machine passed under a year earlier. So if something unexpected were to happen, we'd identify it within the InSAR and be able to alert the operators. And so InSAR is your always-on, eye in the sky throughout the entire project. The second case study I wanted to go through was the Niscemi landslide. So Niscemi is a town in Sicily. It sits on this quite dramatic plateau with these steep slopes. The geology here is sand over clays, and that's what forms this geomorphology. Because the sand is hardened to clay, it means you don't erode from the top, you erode into the clay from the sides, and that generates these steep slopes. Unfortunately, that same geology also makes the area very prone to landslides, because when you have extreme rainfall, that water percolates down into the sandstones, but it can't penetrate any further because of that impermeable clay layer. And so the water tends to sit in the sandstones, weaken the strength of the rock, and eventually you get failure and landslides. And that's unfortunately what happened in January of 2026. On the left-hand side here, we can see a before and after optical satellite image. And you can see this entire block to the south of Niscemi, which is sort of more than a kilometer by kilometer in size, moving by tens of meters. And this is a really dramatic slide. On the right-hand side, you can see an image like that you'll see all around the media associated with this event of the really dramatic headscarp, which demonstrates this kind of 6, 7, 8 meter drop associated with the slide. This was massive. It involved the evacuation of over 1,000 residents. Major access roads like the SP10 and SP12 were closed. Many minor roads are irreparable. Hundreds of buildings were declared unsafe, and the Italian government required to free up emergency funds of 100 million euros. And damages are estimated to exceed 1 billion euros. And so what we wanted to do was investigate whether InSAR could detect precursor signals on a range of spatial and temporal scales, and evaluate if there were any event precursors, what those signals look like, how they vary across the area, and then how InSAR monitoring can play a role in landslide identification. So we looked at signals on a range of spatial and temporal scales, from the headscarp to the whole block, and from days to years. So beginning on the smallest scale, just looking at days at the very tip of the headscarp. This is our displacement map from the 7th of January to the 13th of January. These were the last 2 radar images that were acquired prior to the failure. And what we're looking at here is displacement over just a 6-day period. The displacement is scaled as plus minus 20 millimeters. So these red points, or orange points, represents 1 to 1.5 centimeters of movement in the 6 days prior to the event. And these points are exactly where the headscarp eventually opened up at the southern limit of the town. If you look at this last 6-day period in the context of what came before, we can see that in the 6 months prior, we had some displacement, we had some movement of about 10 millimeters, but that last 6 days represents a real departure from what went before. We actually see this kind of 1.5 centimeter drop in that last 6 days, as shown in the image. So it then begs the question, well, does that mean we could only identify precursors to this landslide with 6 days prior to the events? And to consider that, we can look on the scale of months. So now going back into the Insights platform to analyze the data a bit further, we can see on the top left-hand corner another InSAR specific tool that we have in our platform, and that's this time slider. So while you can look at the whole 6-year data stack that we processed, I mean, we'll do in a minute, at the moment I've formatted the slider so we're just looking between July of 2024 and July of 2025. I'm interested in this time period because I wanted to look at the last time we had extreme precipitation and work out whether there are any precursors that we should have brought into this year, so that when we saw the extreme rainfall coming, we could have known that this was perhaps something that may have occurred. Each point that we're looking at now is vertical displacement. So red is subsidence and blue is uplift. We're able to determine pure vertical motion by using satellites from 2 lines of sight. So we're looking at from two different angles at the area and doing relatively basic trigonometry to calculate the pure vertical motion. Our points are scaled to plus minus 50 millimeters. So the darkest red points represent 50 millimeters of subsidence and blue is 50 millimeters of uplift. Put you in kind of some spatial context, I've overlaid that GIF that I showed earlier over the town. So you can see that the headscarp opened up to the southern limits. It kind of runs through here and everything to the south slid. We can see the town itself had relatively low displacements. We've kind of got all of these light greens. That's telling us that this hasn't moved much during this 12-month period. But on the slope, we see lots of signals, quite strong signals as well, lots of blues and reds. There's a lot going on. It took a little while for me to get my eye in, but once I did, I noticed some really interesting patterns. If we begin by looking at some of these subsidence signals, so we're using our analyst tool, our time series tool, to look at the time series of these 4 points. We can see that we have subsidence of about 35 millimeters. That subsidence isn't linear or constant, actually happens in a few steps, and these steps are associated with the rainfall events. What we find is that if we move just further south, we now see a block of blue points. So what we have is uplift just meters away from where we're observing subsidence. And the uplift points are shown in this blue line here. And that's really intriguing. What's even more interesting is that when you look at the time series, you see that they mirror almost perfectly. They're showing the same pattern, just with opposite polarities. We see an event in kind of March of 25, where we see both of these trends setting off, and then another event in June-ish of 2025. So how can this be? In order to look at this further, I want to demonstrate this using an ancient example on the western side of the town. If we look at this western slope, we can see a number of these lobes. And these lobes represent ancient examples of these landslips. So you can see this kind of rotational movement at the toe of this slide. These are ancient examples. We can see someone's now built an orchard or potentially a farm on top of this sliding lobe. But you can imagine with this rotational component, what you have is subsidence at the top, and then you have uplift at the bottom where the toe of this slide pokes back up. And that's exactly what we have here. We can show it as a transect as well. So if we take a transect of the topography, so that's shown in the green, that's our digital elevation model. And the black line, we have our InSAR above it. Where we have subsidence, upslope, is at the top of this rotational feature. And the bottom, we have uplift, which is associated with the toe of this slump poking back up. So we can look between July of 24 and July of 25 and identify slumps like this that demonstrate this is a highly unstable slope up to 18 months in advance of the event that happened earlier this year. And this isn't the only example. Once I got my eye and I started to notice loads of these pairs. So we see another one here with subsidence upslope, uplift downslope with a mirrored displacement trend. We can see again an event in January and then another in May of 25. We can see one here where again, we've got another in May. And then finally one here, which is where the headscarp eventually opened up. You'll notice a lot of these trends are happening in January and May, and that's because that's when we had the rainfall. And so we could have identified these 18 months in advance and said these are areas where we see lots of these very small rotational slumping events. So this is clearly an unstable slope. So finally, to look at the longest time period, we want to look on the scale of years. You'll see from the top left-hand corner here, we're now looking at the full 6-year data stack. So going all the way back to January of 2020. We're still looking at vertical displacement, and this time it's scaled to plus minus 150 millimeters. So these darkest red points represent 15 centimeters of displacement over 6 years. And if you look at the displacement trend of some of these points, we can see that cumulative displacement, which is significant. And again, that trend isn't linear or constant. We actually have a number of these steps or accelerations. So we can see in 2025, for example, we were flat, then accelerating, then flat again. So this is kind of episodic movement. And we can compare that with precipitation data. So one of the things we can do in our insights platform is incorporate external data, be that weather data or GPS or ground-based radar. So here in the red line, each dot represents precipitation for a given month. And what we can see is that with each step or acceleration in our displacement time series, we see a large amount of precipitation. And this is really reinforcing the idea that rainfall is what drives instabilities on this slope. The last feature I want to outline is towards the south of that block that moved. Here we're actually looking at longitudinal movement, not vertical. So red represents westward movement and blue represents eastward movement. And we can see two distinct areas here that are moving west and east. So they're moving in towards each other. And this has cumulative displacements in the latitudinal plane of about 25 centimeters over 6 years. This again is really serious amounts of movement. So then there's the question of, okay, so why are they moving towards each other? And it makes a bit more sense if you look at it in 3 dimensions. So you can see we've got 2 slopes either side of a river valley, each of which is moving in towards the center of that river valley. Both of these slopes are slumping in to the center of that valley. And that's really important because we have infrastructure like these roads that are running as major networks into the town of Niscemi. And these roads are sat on slopes that are moving 25 centimeters or so over the course of 6 years. We can actually see here again, there's another westward moving patch that straddles the road. And so it's really important for those charged with responsibility for infrastructure networks to understand the slopes on which they're built. So hopefully I've been able to demonstrate with these 2 case studies some of the advantages of InSAR monitoring. We're able to obtain reliable millimetric level measurements of displacement at the surface over large coverage areas. We can monitor in any weather conditions. The GIF that I showed earlier of the landslide using optical imagery, we have to wait for cloud-free days. That's not something we have to wait for with radar imagery. We can get high density measurements. These results were produced using Sentinel-1 data, which is free and open access. And so it's very useful for a lot of these projects, and it has spatial resolution of about 20 meters. There are commercial options that we can get even denser measurements, so 3, even 1 meter spatial resolution, and that's something that we do regularly for clients. The time series here is updated regularly, so we get an acquisition every 6 days or so, and we can add that onto the end of the time series. And we have decades of historical data for baseline studies. If you're interested in historical deformation over a site, you don't have to deploy instrumentation and wait for those results to come in. We can tell you on day 0 what's happened on your site for the last 10 years. It's a fully remote technology, which is really beneficial because it means that it's safe for us when we're looking at areas of geohazards, but it's also makes it very cost-effective technology. And it's also a really good complement to ground-based instrumentation. InSAR isn't necessarily a replacement for ground-based instrumentation, but it means that you could be more proactive with the instrumentation that you deploy. InSAR can highlight areas where you'll want to increase your spatial and temporal resolution using ground-based instruments, but equally we can tell you areas that aren't moving, where that instrumentation will be redundant. So you can be more proactive and get better value from your ground-based. And finally, Catalyst as a company, we offer very bespoke InSAR monitoring to address site-specific objectives and challenges. The 2 case studies I outlined here are in very different geographical contexts. They require different signal processing techniques because of the strength of signal we get back in urban environments versus environments like Niscemi, where you have lots of farmland. We're also looking for different signals and different strengths of signals. And so that requires a bespoke approach to be able to really meet the site-specific challenges. It's not a one-size-fits-all, and that's what we do. The last slide I wanted to finish on was this slide about the infrastructure lifecycle and where InSAR comes in. InSAR provides value across the lifecycle. So beginning with concepts and planning, identifying historical deformation and helping with site feasibility, through to design and understanding how you can integrate InSAR with your ground-based monitoring strategy, Procurement's also a really interesting one because InSAR is a really up and coming technology. You can use it to strengthen your bids, to show a proactive attitude towards monitoring. And also it's a cost-effective component, so it may allow you to reduce your bid costs as well. During construction and operation, InSAR really shines to identify movement during these times. And then finally into aging infrastructure. Especially in the UK, we have loads of aging infrastructure, and actually prioritizing which areas we need to inspect more frequently, which ones need replacing first, is a real challenge. And that's one that InSAR is designed to meet. We can look at wide areas, look across whole asset portfolios, and tell you which of them are showing the greatest displacement patterns, and so allow you to prioritize your maintenance efforts on aging infrastructure. So thank you very much for your time and thank you for listening. I think we're now going to open it to some questions. If anyone has any.
Yeah, thanks, Ben, for walking us through the case studies and demonstrating the applications of Catalyst insights. So I do see some questions in the Q&A panel. We could start with the first one. I see, how do you know what movement is good and what movement is bad?
Yeah, I think that's a really interesting question. So InSAR as a technology doesn't inherently tell you what's good or bad. InSAR just objectively tells you what the displacement is. But I think where we want to add value is to be able to work with clients to understand what kind of movement is good and what kind of movement is bad. Understand your site, what kind of movement you expect. So for example, a lot of the work that we've done with bridges, these have really seasonal signals, and these are built into a lot of the kind of engineering workflows. And so we want to work with clients to understand what's your tolerance, what do you expect them to see? And then when you exceed that tolerances, we can provide you with alerts and more bespoke processing, et cetera. So we kind of work with our clients to understand what they would consider good and bad, and how we can use our InSAR to inform that.
Okay. I see another one. Can we use Catalyst Professional to do InSAR?
Yeah, so unfortunately, InSAR isn't included in the Catalyst Professional software. A lot of the kind of background stuff, the early level processing with radar data is something that is available in the Catalyst Professional. But InSAR itself as the package is something that we do outside of providing in Professional. That's because InSAR is a really difficult technique that requires expertise to work through that workflow. And so it's not offered in Catalyst Professional.
Okay. Which satellites does Catalyst work with?
Yeah, so we work with all satellites. I think as a company, we really pride ourselves on our ability to ingest data from a wide range of satellites. That's kind of the foundation of what our Catalyst Professional software is built on. And that is really great for me as an InSAR scientist because I can leverage this background of ingesting any type of satellite data. I can leverage that and use that for my processing purposes. So we work with a whole range of satellites through from free and open access Sentinel-1 all the way through to high resolution TerraSAR-X, L-band data. So yeah, we sit down with clients, understand their sites, their challenges. We can understand budgets as well. That's really important. Be able to pick out the best satellite for a given site.
Yeah, I can add a little bit more onto that as well. So we're constantly updating the sensor supports of our software, and we do update the sensor support page on the customer center fairly regularly with every release. So we're constantly just adding new sensors, and we already do support most constellations. Let's see, another question we have here is, what is the resolution of each point measured?
Yeah, so I guess there's kind of two questions of resolution. The first of them is spatial resolution, so how far apart the points separated. That's about 20 meters. It depends slightly on the topography and things, but it's about a 20-meter spatial resolution. In terms of the resolution of the time series data, so the actual displacement measurements, in Milan, we were looking at uncertainties of 1 to 2 millimeters because we're in an urban environment. We get really strong responses from buildings, and a lot of these areas that have like right angles, you get these lovely double bounces. So that's a really kind of low uncertainties. In areas like Niscemi, where you've got more vegetation, you're more prone to vegetation scattering of that radar signal. You have larger uncertainties. It's still in the millimeters. Whereas when you get to really vegetated areas, you either don't get results at all or it's centrometric. So the resolution is something that changes based on what your ground conditions are. In an urban environment, you can expect it to be millimetric, and then that grows with difficulty of site conditions like vegetation and things. So in Milan, like very low millimeters. Niscemi is kind of like mid of 5, 6, 7 millimeters, something like that.
Okay, I'm seeing some more questions here, and we still have some time, so I'll read them out. How do you validate results?
Yeah, so the first thing I'd say is that there is a large archive of academic and private sector articles demonstrating strong consistency between InSAR and like ground-based measurements. So we're as a kind of industry, we're very happy that InSAR is matching expectations and independence values. Whereas on a site-by-site basis, it's more difficult to validate results. InSAR is really good for validation because it's usually a very separate data set to, for example, GPS or GNSS or ground-based radar. And so because it's entirely independent, it means that you can compare them and validate. So we often work, for example, with mine sites, looking at their ground-based radar, comparing our results with the ground-based radar, understanding if there are differences, why those differences exist. And so validation is something that we do on a site-by-site basis, depending on what ground-based instrumentation they have available to do comparisons with.
Okay, let's see. There's lots of questions. Ben, are you seeing them on the side on the Q&A?
Yeah, I can see some of these.
Okay.
Yeah.
Which one did you want to answer next?
Yeah, cool. So there's a really interesting question about forecast data and rainfall. So the using rainfall to predict subsidence is very difficult. You'd have to have very strong links between subsidence rates and rainfall amounts, which is something we didn't do here. I'd be interested in seeing any research into that, but I think there's so many components that cause instabilities actually producing an analytical solution for rainfall versus subsidence would be quite hard. Not impossible, but hard. One thing that we do, however, is we produce not just in the InSAR, but lots of optical data sets as well. When we look at, for example, there's loads of Catalyst does loads of stuff like vegetation. So looking at where we've got like tree falling compared to rainfall and wind forecasts and things. Anyway, sorry, there's a bit of a side, but as far as subsidence goes, we can identify areas that are, for example, accelerating in movement. So they're showing accelerated subsidence. And then we can say, well, we're also expecting high rainfall in this area. And so we can start to then flag these areas as concerning, saying, look, we've got this accelerating movement, or we've got really strong relationships between displacement and rainfall. We're now forecasting rainfall in this area. We want to be looking at this very closely. And that's something that we are able to do on for some of our projects, which is that's a really interesting challenge for sure.
Okay.
Also seeing a question about whether radar can penetrate the ground.
Yeah.
So C-band data, which is what we're using here, can penetrate probably kind of like a couple of centimeters. It really depends on what the ground's conditions are. If you've got lots of water or snow or ice, you're hardly going to penetrate at all. The water acts like a mirror, so it just reflects the signal. Whereas if you've got very dry, sandy environment, for example, you can penetrate further. There are options like L-band data, which is much longer wavelength, and that allows you to penetrate further. So with ideal ground conditions with L-band data, you can penetrate kind of tens of centimeters, potentially even up to like a meter. And that opens up lots of ability to map things like soil moisture, leakage, by penetrating the ground. But you are still only looking at kind of centimeter level order of magnitude for that.
Okay, I'm seeing a couple more we haven't answered.
Yes, yeah. The chirps rainfall data, a question about that. So have we used chirps rainfall data to correlate precipitation with subsidence? I haven't used chirps specifically. This was a different publicly available data set of precipitation. But yeah, no, I think that would be a really interesting thing to do. The other benefit of chirps is that you'd be able to look at it at scale. So can we, instead of looking at a single site, look at much larger areas and correlate subsidence with rainfall, I think, or displacement patterns with rainfall? I think that'd be very interesting as well. So potentially that would allow you to do things at scale. But we haven't looked at it per se.
Okay, let's see.
Are there any that I've missed?
Yeah, there's one that says, which satellite series are capable to provide most archive InSAR data today? And I think
Yeah,
there's a
good question.
follow-up to that
Yeah,
right at the
so
bottom.
okay, yeah. So in terms of like the best archive satellite data today, so Sentinel-1 is always the place that we start. That's been going back kind of 10 years or so. So we've got a decade of archive data to look at. That's also really useful because it's still acquiring now and will be into the future. They've just launched like Sentinel-1D, so the fourth in that constellation, which is excellent. It's going to keep going. And that's really good because you can get this whole archive going back kind of 10 years. If we want to go back even further than that, so we can go back to like the 2000s, we can do that using other satellite imagery or radar imagery that has since stopped acquiring. So it is possible to go back to sort of like 2005 or so with radar images from various satellites that you kind of have to tag onto the end of each other. But in the Sentinel-1 satellite is always our starting point because you can kind of start from today and into the future and look back about 10 years. But we can get data going all the way back to the kind of early 2000s.
Okay. Um, what's the most appropriate resolution for archives, such as accuracy, millimeter scale?
So for the most accurate resolution for archive. Yeah, so again, archive data, yeah. So Sentinel-1 gives us that millimetric scale accuracy in most cases, and that 20-meter resolution spatially. Sentinel-1 is probably the only satellite, well, it is the only satellite that has global coverage. So for almost any area of interest, we can generate an archive for. When it comes to the most appropriate, that depends on the site, what they want to achieve. If you want super high resolution data or you want even smaller uncertainties, for example, we can look like X-band, which is smaller wavelength. So especially in urban environments, we can get really low uncertainties. But archive data is limited because that's a commercial option. So they only acquire where they're asked to acquire. They don't just acquire over the whole globe all the time. So the most appropriate archive data, to be honest, is a choice of the ones that are available, which is usually Sentinel-1's a starting point, and then some other commercial satellites, depending on what's acquired there before. But that's something that we don't know until we've looked at a site. So rather than saying most appropriate one and then it turning out that there's not actually any coverage on the site, I wouldn't want to overpromise. But yeah, so I think Sentinel-1 is a starting point, and then whatever else is available, we can assess and give you ideas of accuracy, appropriateness for your challenges.
Okay, and I'm just seeing one final question there. How is InSAR different to LiDAR?
Yes, it's a great question. Yeah, it's one we get all the time. So they're both really valuable approaches. So LiDAR often generates you a digital elevation model, and that is in kind of absolute space. So you know for a given point, it's got an elevation of X. Then when you acquire a second LiDAR model, you can take one away from the other and look at how the ground surface has changed. So you can look at where you've lost volume or added volume. But that kind of approach only has a sort of centrometric accuracy. So if you're interested in millimeter displacement at the surface, InSAR is a much better tool. But InSAR works in relative space. So we assume that you have no displacement on day one, and then we look at displacement relative to that. We never have a kind of absolute starting point as to where elevation was in the first place. We don't work in elevation terms. It's all about movement from this zero starting point. So LiDAR is really good if you want to work in absolute elevation space. If you're looking at centimetric to sort of meter scale changes at the surface, whereas InSAR is much better if you're interested in millimetric displacement. I'd also say that acquiring InSAR data every 6 days is something that's achievable. Doing LiDAR at that frequency would become very expensive. And so InSAR, especially because we use free and open access data, it's a more cost-effective tool for looking at changes to the surface.
Okay. I think we should just give everybody 1 minute to answer the poll.
Fantastic.
And if anyone has any other questions, you could type them in. We can address them while we're waiting. Okay, so that concludes today's webinar. I want to give a big thank you to Ben for sharing his insights into the urban excavation and slope failure cases from recent events. Thank you to everyone who joined today and participated in the poll and the Q&A session. We appreciate your time and engagement. If you have any additional questions, feel free to contact us at sales@catalyst.earth. Your feedback plays an important role in shaping our future improvements for the software, so we encourage you to continue sharing it with us after the session. And thank you all for being a part of the Catalyst Earth community.